sir.
Walaikum salam. Okay, so we have done some 12 examples on this Gauss law, okay, on flux actually, okay. Now, next our next topic is application of Gauss law. Continuous questions are asked on this in NET as well as just examination, okay, or different examination, okay. Continuous questions are asked from here, okay, and that too quite easy questions, okay. ठीक है ना बेटा? So first of all, how we'll start is this application of Gauss law. So calculating electric field using Gauss law. That's our topic, okay. So concentrate here. Okay, so first of all, generalize the technique, how to use the Gauss law. Step down first is that identify symmetry of the electrostatic field. Okay, आपने ये पढ़ा होगा Dave J. Griffith. Okay, so in Dave J. Griffith, the steps are exactly in the similar fashion. Okay, so first of all, step down first is that identify the symmetry of the electric field. And as far I know, there exist only three symmetries. Number one is spherical symmetry. Number second is cylindrical symmetry, and number third is plane symmetry. Fine. Okay. Then step number second is that choose the Gaussian surface. Okay, choice of Gaussian surface depends on the symmetry of the field. For example, if the field is spherically symmetric, like the other point charge, or for example, there is a uniformly charged sphere, in that case, the electrostatic field has a spherical symmetry. When it's spherical symmetry, the Gaussian surface chosen will be what? That will be a Gaussian. That will be a sphere. Okay, Gaussian sphere. And in case the electrostatic field has cylindrical symmetry, then the Gaussian surface will be Gaussian cylinder, and in case it has plane symmetry, then the Gaussian surface will be what we call as Gaussian pillbox. Okay, the choice of the Gaussian surface must be such that number one is that the electrostatic field must be constant at every point on the Gaussian surface. Its magnitude must be constant at every point in the Gaussian surface. Okay, number one. Number second is that this electric field and dA vector, the angle between the electrostatic field and the dA, that is area element, must be either 0 degree or 90 degree, so that the theta is out of the equation. If it is 0 degree, if the theta is equal to 0 degree, then obviously cos 0 is equal to 1, and hence theta is out of the equation. And in case this theta is 90 degree, then the integral will simply vanish, because cos 90 is equal to 0. And it can be 180 as well. Okay, so cos 180 will be equal to minus 1. So again, the theta is not inside the equation. Okay, so we don't want theta in the equation. Okay, that's why the Gaussian, the choice of Gaussian surface must be such that the electrostatic field and the dA vector, they must be either parallel or anti-parallel or mutually perpendicular. Fine. Then step down third is that use the Gauss's law. That is simply flux is equal to integration of E dot dA is equal to enclosed by epsilon naught to calculate the electrostatic flux and hence the electrostatic field. Okay. So we'll be dealing with the application of Gauss law. Once we are done with the application of Gauss law, we'll be doing some examples that have already been asked in the competitive exams that are based on the application of Gauss law. Then we'll be doing some examples on that Gauss's law in the in this differential form. Okay, we'll be doing that as well, studying how to calculate the divergence of the electrostatic field if this electrostatic field is given in the Cartesian coordinates, if it is given in the cylindrical coordinates or the spherical polar coordinates. Fine. Okay, so we'll be doing that as well. Okay, so you concentrate here. Okay, so concentrate on this. So I'm sure ये आपको अच्छी तरह से समझ में आया होगा. And moreover, you must have studied this in the first year of your BSc and in the class 12th as well. Okay. So we'll not have a debate on this. So next let's switch straight with the examples. Okay. So first of all, what we'll be doing is this. We'll be doing the examples on spherically symmetric fields. Okay. So here I will write down the spherically symmetric fields. अच्छी तरह से ध्यान रखना. Spherically symmetric fields. Fine. So spherically symmetric fields. Spherically symmetric fields. Electrostatic fields. Fine. So spherically symmetric field. अच्छी तरह से ध्यान रखना बेटा. And the simplest example of the spherically symmetric field is a point charge. The electrostatic field due to the point charge is what? That's spherically symmetric. So spherically symmetric fields will be starting with this. Okay. So question number one is that point charge. Fine. Okay. So that's not important. Really never important. Okay. But we'll do it quickly. Okay. So point charge. You know the electrostatic field due to the point charge, isn't it? You know the electrostatic field, and you can safely plot the graph as well. Okay, so simply there's the point charge. So simply I will write down straight away electrostatic field will not be used by Gauss law. That is childish. Okay, so electrostatic field will be simply equal to what? That's equal to K multiplied by Q divided by R square. Then if you want to write down the vector form, then here you can write down R K. Isn't it like this? K divided by R square multiplied by R K. So this is the electrostatic field due to a point charge. This in turn implies that the electrostatic field is proportional to 1 divided by R square. And in case you want to plot the graph, E versus R graph, that will be a rectangular hyperbola, isn't it? Okay, so the graph will be rectangular hyperbola. Okay, now concentrate here. So graph will be simply a rectangular hyperbola. So here we are. So the graph is simply a rectangular hyperbola. You want to plot the graph, you can safely plot the graph. So we have already done this. Okay, so along the x-axis I will take r, the radial distance. Along this I will take the electrostatic fields. This is proportion 1 divided by r square. So as a graph implies that it will intersect the horizontal axis and the vertical axis at infinity. Fine. So this is proportional to 1 divided by r square. You can write like this, number one. And number second is that as r tends to infinity, this electrostatic field tends to 0. Okay, this is intercept, one intercept taken at infinity. And another intercept is that r tends to 0. The electrostatic field tends to infinity. Okay, this is a Dirac delta function. Sorry, it tends to infinity. Taken out, this is a Dirac delta function. We'll be discussing Dirac delta function in length and breadth. Okay, Dirac delta function and step function. ठीक है ना बेटा, तो इसी तरह से यहाँ ध्यान रखना. Okay, so this electrostatic field what due to a point charge. Okay, so we are done with this. Next is that for example there is what, अच्छी तरह से यहाँ ध्यान रखना बेटा. Okay, so question number 2 is like this. We want to calculate what electrostatic field. अच्छी तरह से ध्यान रखना बेटा. Electric field due to uniformly charged hollow sphere. Uniformly charged HS. HS implies what? Hollow sphere. ठीक है ना बेटा? Or it can be like this as well. Or it is this uniformly charged hollow sphere or conducting solid sphere. Conducting solid sphere. ठीक है ना बेटा? Conducting solid sphere. Okay, so in case of conducting solid sphere, if a charge is given the conducting solid sphere, whether it is solid or whether it is hollow, the charge will reside on its surface. Fine. It's like this. For example, here we have this is a sphere. Now the sphere can be, if it is hollow, non-conducting, then the charge is given to it. Obviously, the charge will reside only on the surface because there is no meat inside. When there is no meat inside, so there cannot be charge inside. Okay, wherever there is a charge, there is matter. The charge cannot exist without the matter. Fine. Okay, so if it is hollow, so simply the charge will reside only on its surface. So the charge is going to reside only on its surface like this. Okay, so this here positive charge is placed here and its radius is equal to capital R. Fine. Okay, now the charge is residing here. Okay, now for example, if it's conducting sphere, it can be conducting hollow sphere, conducting solid sphere. In both the case, the charge will reside only on the surface. Now, if it is conducting solid sphere and charge is given to this, the charge will reside only on the surface. Why? What is the reason for that? Bolo beta. Question आया समझ में? Question is like this: if this sphere is a solid and conducting, like it's a metallic sphere, for example, made of iron, and the charge is given to it, the charge will surely reside only on the surface. Inside the charge will be simply equal to 0. Why? What's the reason for that? Bolo beta. Hello? Are you able to understand or not? Beta, question ये है, if for example there is a solid conducting sphere implies that there is a meat inside as well. Okay, inside there is meat. Fine. But the charge is given to it, the charge is going to reside only on the surface. Why the charge resides only on the surface? Why cannot the charge reside inside as well? Why the charge resides only on the surface? Why? What's the reason for that? Can anyone answer that? Okay, let me answer it. Repulsion is not the reason. Repulsion is not the reason.
Potential.
देखो
Potential minimum.
Repulsion cannot be the answer. Okay, there's it's mentioned the David J. Griffith अगर आप अच्छी तरह से David J. Griffith पढ़ोगे तो वहाँ पर ये important concept in the form of question it is there. That's like this: if there is a solid conducting sphere and charge is given to it, the charge resides only on the surface. It seems to us as if the meat of this sphere is wasted. It gets wasted. Why the charge cannot reside inside? Why the charge resides only on the surface? And most of the students answer that there is force of repulsion with the charged particles, and as a result of which the charged particles reside on the surface. Okay. Now imagine like this. Repulsion is not the reason. Why? Suppose that let's suppose that there are some 2 million charged particles on this sphere. Some 2 million charged particles. Fine. Okay. Now these 2 million charged particles are residing on this 4 pi r square. They are residing on the surface, means that they are residing on 4 pi r square. Okay. Now let's imagine the situation like this: 1 million charged particles placed on the surface and 1 million charged particles are scattered inside. They are scattered inside. Now, do you think that the average separation between the charged particles is going to increase? Okay. In the situation number first, in the scenario number first is that the charged particles are only on the surface, 2 million charged particles. The separation will be obviously less. The charge density will be larger. The force of repulsion will be larger. Now, for example, what we do is this: we'll put this 1 million charge particles inside the meat. When we put the 1 million charge particles inside the meat, so obviously the average separation between the charge particles is going to increase. Sorry, average separation will increase, and hence the force of repulsion between any two charged particles is going to decrease. Okay, so the common sense says to me that the charged particles must reside inside as well as on the surface. They must reside inside as well as surface. Okay, so that means the force of repulsion cannot be the reason. Had the force of repulsion been the reason, then in that very case the charge particle should have been inside as well, so that the force of repulsion is minimized. Okay, so that's not the reason. Now what is the reason? The reason is this: that's electrostatic potential energy. That is a concept, electrostatic potential energy. Okay, let's suppose like this: there are two different situations. One situation number one is that there's a conducting solid sphere. Okay, charged particles reside only on the surface. And then there's a conducting solid sphere, and let's imagine that it's a hypothetical situation that the charged particles are inside as well. In both the cases, we'll calculate electrostatic potential energy. Okay, what we'll come to know is that the electrostatic potential energy is more when the charged particles are on the surface and inside as well. Compute that system, and the charged particles are only on the surface. In that very case, so like this it is. For example, here we have this one sphere and this another sphere. The dimensions are exactly same. In this very case, charged particles reside only on the surface. In this very case, the charged particles reside inside as well as on the surface. They reside inside as well as on the surface. Fine. Okay, we'll calculate the electrostatic. Later on, you'll see. We'll be calculating this potential energy. Okay, obviously. And the potential energy here that comes out to be here in this very case, it comes out to be for this potential energy is equal to, it has a lesser potential is 1/2 multiplied by K into Q squared divided by R, where Q is the charge on this, R is the radius of this, and K is electrostatic constant. Fine, R is radius. Okay, so Q is charge of this. Fine, and the potential energy when you will calculate of this system, it is equal to 3 divided by 5 multiplied by KQ squared by R square. Sorry, KQ squared divided by R. It is equal to this. KQ squared by R. Fine, this is the potential energy. Okay, now this is for example the potential in the system number first, and this is the potential energy of the system number second. Now compare the two. So obviously this is 1/2 is 0.5, 3/5 is 0.6. So that means this potential is greater. So that means U second is greater compared to U first, which in turn implies if we compare these two systems, so this is a greater potential energy and this is a lesser potential energy. Okay, and a system always wants to be in that position, in that state in which its potential energy gets minimized. That is the reason the charged particles go to the surface. Okay, they get pushed towards the surface. That's the reason. So as to minimize it, this system switches to this system. Why? What's the reason? The reason is that in doing so, its potential decreases from 0.6 times all this to 0.5 times all this. Fine. So that's the reason. That means this is the minimum potential energy. Okay, so we'll be calculating this potential energy later on. Okay, now for example, if we have now non-conducting or insulating sphere, you are giving charge. The charged particles, they will reside on the surface and they will be inside the meat as well. In that very case, how to define this potential energy theory? In that very case, what actually happens is that the charged particles are inside the meat and those charged particles are desperate to move to the surface. But actually it's an insulator, so there's no pathway by which the charged particles can move to the surface. In case of conductor, there's a pathway by the charged particles can move to the surface. But in case of insulator, there's no pathway by which the charged particles can move to the surface. Fine? So I think that this is now clear for you. So repulsion cannot be the reason. Had the repulsion been the reason, that in that way, this system is more suitable compared to this system. So potential energy is the reason. Okay, so there's a problem done on David Griffith, and he explained it clearly. Okay, now here we are. So Gauss law, back to Gauss law. So this conducting solid sphere, charge is given to it. The charge will reside only on the surface. If it is solid conducting or hollow conducting, in both the cases the charge will reside only on the surface. And if it is insulating, then it has to be hollow sphere, so that the charge is only on the surface. Now we are supposed to calculate what? Electrostatic field. Like this, I will make it here. So this is here, this hollow sphere. So this here positively charged. Fine. Like this it is. Okay. David Griffith for example that is before Gauss's law. He is trying to calculate the electrostatic field without using the Gauss law by the integral method. Okay, that is the advantage of the Gauss law over the Coulomb's law, or the integration method. What Gauss law does actually is that it simplifies the integration. Okay, it highly simplifies the integration. But there the disadvantage of the Gauss's law, and the disadvantage is that you can use the Gauss law to calculate electrostatic field only for the symmetric fields. If, for example, the field is not symmetric, like for example, there is a uniformly charged ring, you cannot calculate the electrostatic field due to the uniformly charged ring using Gauss's law. Why? What is the reason? The reason is that its electrostatic field has neither the spherical symmetry nor the cylindrical symmetry, nor the plane symmetry. That's why we're not able to use. So that means the Gauss law is not a generalized technique. It is used only in case of symmetries, only if the electrostatic field has a symmetry, has spherical symmetry, plane symmetry, or cylindrical symmetry. That's the problem with the Gauss law. But the good thing with the Gauss law is that it's easy to handle. Okay, so this is here. This secure here, okay, its radius is capital R. Now directly you can write down the electrostatic field inside. Obviously it will be equal to 0, isn't it? When small r will be less than capital R, so electrostatic field is equal to 0. Then electrostatic field will be equal outside, it will be equal to same as the point charge, kq divided by r square. Suppose you want to calculate electrostatic field at this period point, which is at a distance of small r. Okay, so small r is greater than capital R, it's equal to kq by r square, same as the point charge. Okay, so this is true when small r is greater than capital R. Okay, you don't have to calculate it as well. If you are interested, you can simply calculate integration of E dot dA like this. You can use the Gauss law, that's integration of E dot dA will be equal to Q enclosed by epsilon naught. Okay, for example, there is a point which is inside here, somewhere here. Okay, this is the point. Now you want to calculate electrostatic field here, so you choose a Gaussian secure like this. The charge enclosed is 0, hence the electrostatic field will be also equal to 0. Outside, the charge enclosed simply equal to capital Q, so the electrostatic field will be equal to this. Okay, so हमें इसकी derivation कोई जरूरत है ही नहीं. So electrostatic field is simply like this. Inside, electrostatic field will be equal to 0. Outside, electrostatic field is same as that of point charge. Okay, so that means outside the electrostatic field is as if the whole charge of the sphere is concentrated at the center of the sphere. Right? Okay, so next is that we have to plot the graph. So safely we can plot the graph. There's no rocket science in it. So safely we can do it like this. इसी तरह से ध्यान रखना बेटा. We can do it like this. For example, here we are along the horizontal direction, there is R, and along the vertical direction, that's electrostatic field. Okay, electrostatic field. Then at the center, electrostatic field is equal to 0. Up to the surface, the electrostatic field is equal to 0. Then from there onwards, the electrostatic field becomes like this. So it is proportional 1 divided by R square. That means the graph will be rectangular hyperbola. Okay, so the graph is rectangular hyperbola. Okay, so the graph will be rectangular hyperbola like this. So the graph will be like this. Okay, so here electrostatic field is equal to 0 inside, and outside it's proportional to 1 divided by R square. Okay, and here small r is called capital R. Then here is the point. This here electrostatic field which is maximum, and this will be equal to K multiplied by Q divided by capital R square. So electrostatic field is maximum just outside the surface. Just inside it's equal to 0. And then thereafter the electrostatic field, it is proportional to 1 divided by R square. Okay, so I'm sure ये example आपको अच्छी तरह से समझ में आई होगी. Okay. Next, look at next. Now there is example number 3. Is that example number 3 is like this. We want to calculate electrostatic field due to solid. Here I will write down solid non-conducting sphere. So solid non-conducting sphere. Solid non-conducting sphere or insulating sphere. What we mean by solid non-conducting or insulating implies that the charge will reside on the surface and in the medium. Okay, and we are supposed to calculate electrostatic field. So obviously in this very case, electrostatic field inside will be equal to what? That will be non-zero. Fine, like this it is. Okay, so here we have this, for example, a solid sphere. Okay, so charge is here. This is positive charge here. Okay, like this it is. This positive charge sphere. Its radius is equal to capital R. So radius is given to you, that's equal to capital R, and the charge inside that's equal to Q. That's equal to Q. It's uniformly charged. Fine, and we have to calculate electrostatic field inside as well as outside. Up there, beta. So how we calculate electrostatic field inside as well as outside? Okay. So like this is first of all electrostatic field outside. So here I will write an A part. What is that when small r is greater than capital R, which implies outside. You want to calculate electrostatic field outside. It will be simply proportional 1 by R square. So it will be simply equal to KQ divided by R square. That means electrostatic field outside is always proportional 1 by R square, whether it's hollow sphere, whether it's solid sphere, whether it is uniform or whether it is non-uniform. So that means the electrostatic field outside is not sensitive to what's happening inside. Inside it can be hollow, since the electrostatic field outside will be proportional 1 by R square. If electrostatic field is solid, simply it is KQ by R square. If it is shell, whatever it is, electrostatic field outside will be always proportional 1 divided by R square, or it's called KQ by R square. That means the electrostatic field outside is same as that of the point charge. Fine. Okay. B part is that you want to calculate electrostatic field inside. Now small r is less than capital R. Okay. Let me derive it out. So quick derivation, I will show it here. For example, here we have a sphere. Okay. Its radius is equal to capital R. Now you are interested in calculating electrostatic field. Suppose at this point. Okay. So this lies inside. So this is a Gaussian sphere. Now the charge is somewhere here. Okay. So charge is outside and inside this Gaussian sphere is there. Okay. Now electrostatic field at this point. For example, here we have point P. And we we are interested in calculating electrostatic field at this point P. Okay, so electrostatic field at point P will be contributed by only this charge that lies inside by this charge. Okay, by this shell. Okay, by this pulp and not by the shell. You can get electrostatic field at this point. Okay, so you want to calculate electrostatic field. What you will do is this: you use the Gauss law. Integration of E dot dA is equal to Q enclosed by epsilon naught. Is equal to Q enclosed by epsilon naught. Fine. You can have that. Okay. Now in this very case, Q enclosed is not equal to Q. That's not equal to 0. That is less than Q. Okay. So this is the amount of charge which is equal to Q. Okay. Which is the Q enclosed. So we'll be able to calculate that. Now this integral simply becomes what? It is equal to integration of E dA cos 0 degree. E dA cos 0 degree. So E dA cos 0 degree. Why? Because for example, at this point, electrostatic field will be the radially outward. So this is the direction of the electrostatic field, and this will be an area vector. So area vector is also along the same direction. So the angle between E and dA is 0 degree. So cos 0 will be simply equal to 1. Then it will be in turn equal to Q enclosed by epsilon naught. So cos 0 is equal to 1. So this will be electric field is constant. So pull it out. Integration of dA, that's simply surface area of Gaussian sector, which will be equal to 4 pi r square. This will be equal to 1 by epsilon naught, Q enclosed by epsilon naught. Now we are interested in calculating Q enclosed. Since the charge density is uniform, that means the rho that's uniform, rho is equal to Q divided by V, where Q is the total charge and V is the total volume. That will be in turn equal to Q enclosed divided by V enclosed. That's in turn equal to Q enclosed by V enclosed. So from here you can calculate what's the value of Q enclosed. That will be in turn equal to Q divided by V multiplied by V enclosed. Okay, so let's calculate this Q enclosed. So how much is Q enclosed? That will be equal to Q divided by V. So Q के बदले लिखेंगे Q. V is equal to 4 divided by 3 pi r spherical volume. And V enclosed is the volume enclosed by Gaussian sphere whose radius is small r. So its volume will be obviously 4 divided by 3 pi small r cube. So we have this, that is Q enclosed will be equal to Q r cube divided by capital R cube. This is Q enclosed. Then substitute it here. And we are able to calculate electrostatic field. So electrostatic field क्या आएगा? It is equal to E multiplied by, okay, E will be equal to what? That will be in turn equal to, so here it is Q enclosed, sorry, it's like this. It's equal to Q enclosed by, so I will write like this. That electrostatic field will be how much? Electrostatic field will be equal to Q 1 by 4 pi r square multiplied by Q enclosed divided by what? Divided by epsilon naught. Is it? Divided by epsilon naught. Okay. So here it is. Divided by epsilon naught. Okay. So 4 pi r square. Then here it's epsilon naught. Okay. Then what you can do is this. You can replace this Q enclosed. So it will be electrostatic field will be finally equal to this. अच्छी तरह से ध्यान रखना बेटा. 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Then the numerator it is there is 1 by r square. So here I will write down 1 by r square. Q enclosed के बदले लिखेंगे Q multiplied by small r cube divided by capital R cube. Then this r square will cancel with this. So what we have is this 1 by 4 pi epsilon naught is in turn equal to K multiplied by Q small r divided by R cube. So this is the electrostatic field inside. Okay, this is the electrostatic field when small r is less than capital R. And it is less than capital R. This is the electrostatic field which is called KQ small r divided by R cube. अब देख लो बेटा जुगाड़. अच्छी तरह से यहाँ ध्यान रखना बेटा. Okay, so what is the जुगाड़? So here I will write down shortcut technique. तो ध्यान रखो बेटा. Okay, so shortcut technique simply like this. This is solid sphere. क्या है बेटा? This is solid sphere. Charge is given to it. The charge will reside inside the bead and on the surface as well. Fine. First of all, point number 1 is that the electrostatic field will be always outside KQ by R square. Whatever inside it is, it will be always KQ by R square outside. Fine. Proportional 1 divided by R square. Point number 1. Point number 2 is that at the center point, electrostatic field will be equal to 0. As you move from center to surface, the electrostatic field is going to increase. Why? What is the reason? The reason is this: as you move from center to surface, the charge enclosed by the Gaussian surface will increase, and that will be directly proportional R cube that Q enclosed. So that means electrostatic field is for sure going to increase. So it will be like this: KQ multiplied by small r, directly proportional R. Now this equation and this equation must have same dimensions. अगर यहाँ numerator में R आएगा, so denominator में R cube होना चाहिए, capital R cube. ठीक है ना बेटा? Only then this and this has same dimensions. Okay, now its dimensions are KQ by R square. What are the dimensions of KQ by R square? Will be the dimensions of KQ and small r by R cube. Okay, so this and this have same dimensions. ठीक है ना बेटा? Point number 3 is that at the center point, electrostatic field will be equal to 0 when small r is equal to 0. So at the center, electrostatic field is equal to 0 as expected. Point number 4 is that on the surface, electrostatic field is maximum. So at the center, electrostatic field is 0 As you move from center to surface, electrostatic field increases, becomes maximum at the surface. Then as you move from surface onwards, okay, surface to outside, electrostatic field will decrease as 1 by r square. So on the surface, it will be simply equal to kq divided by Kepler square. You can substitute the small r equal to Kepler here or here as well. You can beta, it will become kq by r square, and this is the maximum electrostatic field, and this is when small r is equal to capital R. Now safely you can plot the graph. If you want to plot the graph, safely you can plot the graph like this. It is. So the graph you can plot is like this. So along the horizontal direction you will take small r, and along the vertical direction what will take is this electrostatic field. Okay, so at the center electrostatic field is equal to 0, then it increases linearly like this, and then decreases as 1 by r square like this. Okay, so this is the graph, and the electrostatic field is maximum when small r is equal to Kepler. और वो electrostatic field कितना है बेटा? That's equal to k multiplied by q divided by Kepler square. Fine. Moreover, what you can do is this. For example, this question is asked in the competitive exams, but the answers are in terms of the charge density. Safely you can do that as well. Okay, so that this is how you can do that. अच्छी तरह से ध्यान रखना बेटा. Okay. So this is the way you can do that. Okay. So you can write down this electrostatic field in terms of charge density. So here I will write down in terms of rho. For example, rho charge density q is not given to us, but rho is given to us. So you can calculate that. What you will do is this rho is in turn equal to charge per unit volume. So that will be equal to q divided by 4 by 3 pi r cube. So simply this implies that you can replace q by what? That will be equal to rho multiplied by 4 by 3 pi r cube. 4 by 3 pi r cube. Okay. Now if you are interested in electrostatic field, so electrostatic field will be this. It will be equal to rho divided by 3 epsilon 0. So electrostatic field, first of all, let's calculate the electrostatic field inside. So it will be equal to rho r divided by 3 epsilon naught. It will be something like this. Rho r divided by 3 epsilon naught. This is true when small r is less than Kepler. If you want to derive it out, you can safely derive it out. How you will derive it out? You will derive it like this. So this is the electrostatic field what outside. K के बदले क्या लिखेंगे बेटा? 1 by 4 pi epsilon naught. Q के बदले क्या लिखेंगे बेटा? Rho multiplied by 4 by 3 pi r cube. Okay, then play with the numbers and calculate the electrostatic field. Finally, it will be like this: rho r divided by 3 epsilon naught. And electrostatic field inside will be equal to rho divided by 3 epsilon naught. It will be as such. This constant will be as such, and you know that outside it is proportional 1 by r square. So यहाँ लिखो r square और यहाँ numerator में आएगा Kepler cube. So that again this equation and this equation are dimensionally correct. Here the dimensions of r are L1, and the dimensions of here r cube divided by r square will be also equal to L1. So this is the electrostatic field when small r is greater than Kepler. I'm sure ये भी आपको अच्छी तरह से समझ में आया होगा. Okay, because this question can be asked in the competitive exam in terms of rho or in terms of q. So I'm sure ये भी आपको अच्छी तरह से समझ में आया होगा. Okay, so we are done with number 1. Example number 1 is that the electrostatic field due to the point charge simply kq by r square. Electrostatic field due to the hollow sphere, inside 0, outside proportional 1 by r square. So outside it's kq by r square. And then the electrostatic field to the solid sphere, it is equal to kq by r square outside, and inside will be kq into small r divided by Kepler cube. So graph we have plotted, then we have written down the electrostatic field in terms of charge density as well. So I'm sure यहाँ तक आपको अच्छी तरह से समझ में आया होगा. Okay, there is no rocket science in it. Okay, next देखो बेटा, next is that exam question number. For example, we have question number 4, and question number 4 is non-uniform solid sphere, non-uniform charge density. The charge density is non-uniform. So here I will write down non-uniform charge density. Okay, in NET in December 2011 there is a question asked on this, so we will be doing that example as well. Non-uniform charge density. Non-uniform charge density. In that very case, you are supposed to calculate electrostatic field both inside as well as outside. So देखो बेटा. Okay, so if it is non-uniform charge density, then in that very case, for sure this rho will be given as a function of r. Rho must be given as a function of r. Okay, so that means it's like this. For example, we'll do an example like this. So rho is given, it's equal to constant. Suppose that constant is something like alpha multiplied by r. It's something like this. Rho is called alpha multiplied by r. Okay, this is solid sphere here. Fine, and it is charged like this, and the charge density is given to you. That's called alpha multiplied by r, where alpha is simply a constant. Alpha is a constant. Okay, and what you are supposed to calculate is this. You will have to calculate what is the electrostatic field both inside as well as outside. Electrostatic field is equal to what when small r is less than Kepler and when small r is greater than Kepler. Okay, so let's try it out. अच्छी तरह से ध्यान रखना बेटा how we will do it. Okay, so again we will use the Gauss law. Gauss law is simply like so. A part is that let's calculate the electrostatic field inside. Small r is less compared to Kepler. Okay, there is no other way around except integration. You will have to integrate this function. So it will be like this: integration of E dot dA will be equal to Q enclosed by epsilon naught. Q enclosed by epsilon naught. ठीक है ना बेटा? Q enclosed by epsilon naught. Okay, this will be simply equal to E multiplied by 4 pi r square, isn't it? Because the rates of the Gaussian sector, that's called small r. So E and D, they are parallel to each other. So it will be cos 0, that is equal to 1. So E is constant everywhere. Pull it out. Integration of D is simply 4 pi r square. This will be equal to Q enclosed by epsilon naught. So here it's 1 by epsilon naught. And Q enclosed can be safely written like this. It is equal to rho multiplied by d tau or dd. One and the same thing. Like this it can be written. Okay? Like this. The reason is this. This rho can be, we can write like this. This charge density is equal to dq divided by d tau. dq divided by d tau, while d tau is what? That's volume element, or you can replace it by dv as well. Then from there you can write this dq, it is equal to rho into d tau, isn't it? And you must know the spherical volume element. This d tau is what? It's spherical volume element. The spherical volume element is in turn equal to 4 pi r square multiplied by dr. You can write 4 pi r square multiplied. Actually it is equal to r square. Actually it is like this. It is actually equal to r square multiplied by dr, r square dr into sine theta d theta into d phi. Okay, but when we will be integrating this d phi from 0 to pi, it will be 2 pi. When we will be integrating the sine theta from 0 to pi, it will be equal to 2. So 2 into 2 pi, that's equal to 4 pi. That's why I have written down directly. It's equal to 4 pi r square into dr. Okay, so this is actually what? Spherical volume element. So here I will be substituting it. It will be like this: electrostatic field multiplied by 4 pi r square. 4 pi r square. Will be equal to what? That's equal to 1 by epsilon naught. Okay, so here it is 1 divided by epsilon naught. Okay, rho is not constant, so that's non-uniform, but it's given as function of r. So rho के बदले में लिखूंगा बेटा alpha into r. d tau के बदले लिखूंगा 4 pi r square into dr. Fine. And the limits of integration of small r will be from 0 to small r. Why from 0 to small r? Because we are interested in calculating electrostatic field inside. And inside the charge will reside, or the charge is like this. It's actually like this. Here we have a solid sphere. So here we have a solid sphere like this. And we are interested in calculating electrostatic field somewhere here. This point. Okay, so this will be the Gaussian surface. Okay, and the electrostatic field at this point will be contributed by only this charge. Okay, only by this charge. So the limits of integration will be from 0 to this small r. So this here small r equal to 0 and this small r equal to r. So that's why the limits of integration are here from 0 to small r. Then electrostatic field E multiplied with 4 pi r square. It will be in turn equal to, here it is alpha, 4 pi alpha is a constant, pull it out, divided by epsilon naught. Fine. Then integration of r into r square is r cube. So the integration I give it r is for 4 by 4. It will be simply r is for 4 by 4. And lower limit will vanish, upper limit will be r. So simply it's r is for 4 divided by 4. Fine. This 4 pi will cancel with 4 pi, r square will cancel with r square. So electrostatic field will be simply equal to this. It will be here alpha into r square divided by 4 epsilon naught. This is the answer to the problem. Alpha r square divided by 4 epsilon naught. So this is electrostatic field which is inside directly proportional r square. This is true when small r is greater than capital R. Okay. Now the electrostatic field is directly proportional to r square. So what does that mean? That means this electrostatic field inside is proportional r square. Now why is it proportional r square? Okay, if it is uniform, then directly proportional r. If it is hollow, then 0. But if it is directly, if the charge density here, you see the charge density here. The charge density here, the question is like this: charge density is directly proportional to r. So that means the electrostatic field inside, it will increase because the charge enclosed by the Gaussian surface will increase. Number one. Number second is that the rho is in turn increasing. It's itself increasing as proportional to r. So that's why the electrostatic field increases as r square. Okay. Reason number one is that the charge enclosed by the Gaussian surface will increase and will be directly proportional to r. The charge enclosed will be directly proportional to r. Number one. Number second, the charge density itself is directly proportional to r. That's why the field is proportional to r square. Okay. So this is the reason. And then number next is that B part is that you want to calculate what? Outside. So outside implies small r is greater than capital R. So exactly same equation will be there. Okay, so exactly it will be like this: integration of E dot dA again will be equal to what? Q enclosed by epsilon naught. Q enclosed divided by epsilon naught. Okay, so it's like this. So this will be again equal to E multiplied by 4 pi r square. E multiplied by 4 pi r square. Then this integration will be exactly similar with the difference, with slight difference. So it will be something like this. Again, it will be like this. This here 1 by epsilon naught integration of rho multiplied by d tau के बदले लिखेंगे 4 pi r square into dr. The only difference will be the limits of integration from 0 to capital R. 0 to capital R. Why from 0 to capital R? Because we are calculating the electrostatic field outside. So when we are interested in calculating electrostatic field somewhere here outside, so we are interested in calculating electrostatic field outside. So the The electric field at this point will be contributed by this charge from 0 to capital R. That's why from 0 to capital R. This will be the Gaussian surface, this one. Its radius is small r, so that's why on the right hand there is what 4 pi small r square, but in the LHS there will be what in the RHS. This is LHS. On the LHS there is small r, on the RHS there is capital R. Why capital R? Because the charge enclosed is from 0 to capital R, and the electrostatic field will be contributed by the entire charge. ठीक है ना बेटा? तो यहाँ क्या आएगा बेटा? Okay, so the E multiplied by, here I will write it down, 4 pi small r square, and here it will be equal to 4 pi multiplied by, okay, rho will be replaced by alpha into r, so there will be alpha outside divided by epsilon naught as well. ठीक है ना बेटा? 4 pi epsilon naught. Okay, so here it's like this, 4 pi alpha epsilon naught. Then इसके बदले r, then r cube, so it will be r is power 4. So finally it will be r is power 4 by 4. Capital R is power 4 by 4. Lower limit will vanish, upper limit will be capital R. Okay, so r is power 4 by 4. Fine. So again, this 4 pi and 4 pi is going to cancel. So the electrostatic field becomes equal to this. So here it is electrostatic field multiplied by r square. 4 pi and 4 pi will cancel. Okay, तो बचेगा क्या यहाँ? So this will be here alpha r is power 4. इसी तरह से ध्यान रखना बेटा, alpha r is power 4 divided by 4 epsilon naught. Okay, so the electrostatic field finally will be equal to this, alpha r is power 4 divided by 4 epsilon naught multiplied by small r square. So this implies that electrostatic field outside is proportional 1 by r square, again as expected. So what I want to say is this: electrostatic field outside will be always proportional 1 by r square, whether it is point charge, whether it is hollow sphere, whether it is solid sphere uniform, or whether it is solid sphere non-uniform. In all these cases, electrostatic field outside has to be proportional 1 by r square. ठीक है ना बेटा? So here I am going to summarize this. Here I am going to summarize the result that rho was equal to alpha multiplied by r. Electrostatic field inside is directly proportional r square. तो वो कितना निकला? That's equal to this. That's equal to alpha into r square divided by 4 epsilon naught. This is true when small r is less than capital R, and outside it is equal to this. It is equal to alpha r is power 4 divided by 4 epsilon naught multiplied by small r square. This is true when small r is greater than capital R, isn't it? So this is the electrostatic field. Okay. Now next is that you can plot the graph as well. You want to plot the graph, so you can safely plot the graph. So electrostatic field at the center must be 0. There's no doubt about that. So at the center it is equal to 0. तो यहाँ 0 आएगा, यहाँ 0 आएगा. Then inside is directly proportional r square. So the graph will be a parabolic graph, not straight line but parabolic. Then outside a rectangular hyperbolic like this. It is something like this, and this will be a small r equal to capital R. And electrostatic field at this point will be how much? So this here E versus R. So put small r equal to capital R. तो क्या आएगा? Alpha capital R square divided by, it will be here alpha capital R square divided by 4 epsilon naught. So this is the electrostatic field on the surface. ठीक है बेटा? So I'm sure ये example भी आपको अच्छी तरह से समझ में आई होगी. Okay. So next example जो है ना बेटा, again it's non-uniform but it's asked in net decimal. Wait a second. Let me write down this example here. Example is like this. अच्छी तरह से ध्यान रखना बेटा, and I'm sure you must be able to do it. Okay, so you have to do it. Okay, so this is the next example, and this example is asked in. Here I'm going to write it down. This example is asked in net December 2012. This question is asked in net December 2012, and the question is like this: that the cylindrical shell, spherical shell like this. This is a spherical shell. Its inner radius is A and outer radius is B. That means from small r equal to 0 to A, there's a cavity. Okay, charge resides only in this small r equal to A and small r equal to B. Okay, the charge density here that is given to you. Here the charge density is given to you, rho, that's equal to K divided by R square. K divided by R square. Okay, now you'll have to calculate magnitude of electric field. You'll have to calculate what is the value of electric field for small r greater than A. We'll have to calculate what's the electrostatic field for small r in this region and in this region for small r greater than A. That means you will have to calculate the electrostatic field between small r equal to A and small r equal to B and r greater than B. You will have to calculate the electrostatic field in these two regions. For example, in the region number first and the region number second. Okay, so calculate electrostatic field in the region number first and calculate the electrostatic field in the region number second. This will stay as a home assignment for you. Okay, so we are running out of time. So that's it for today. Okay, so you take care of yourselves.